Friends, let us discuss the 10th lecture titled Environmental Loads, second part of the online course on offshore structures under special loads. We are discussing the complexities which arise from the conventional loads before we understand the special loads and the responses of offshore platforms under the special loads. In the last lecture, we were discussing about Airy's linear wave theory and complexities arise from the linear wave theory. In case of regular waves, it is a practice to choose an extreme wave to represent the effects of the set of irregular waves. So, the chosen, let us say, special regular wave, which is an extreme wave, is governed by two parameters, namely the wave height and the wave period. However, we agree that random wave is described by the energy density spectrum random waves are generally used for design of offshore structures. When we understand this, there are some basic terminologies which we will understand in connection to the random wave. Let us say short term record length, which is Ts, which indicates the duration of the storm. Significant wave height, Hs, which is average height of highest 1/3 waves. In a short term record, root mean square, that is RMS of wave height, which I call H RMS. This is root mean square value of individual wave heights in a short term record. The fourth one is peak frequency, which is omega 0, which is the peak frequency of the spectrum. Significant wave frequency, which is omega s, which is the average frequency corresponding to or corresponds to the significant wave height. In a short term record. Mean frequency, which is omega bar, which is mean frequency of the individual waves in short term record. Having said this, the most conventional spectrum used for estimating wave forces on offshore platform is Pearson-Moskowitz spectrum. Famously known as PM spectrum. We have an interesting relationship between the peak frequency and significant wave height, which is given by peak frequency is 0.161 G by Hs. So, if I know one, can always find the other. One can also discuss and describe the peak frequency in terms of mean wind speed, which I call as UW. So, peak frequency can also be given by 2/3 G by UW. So, one may be interested why we are looking about the peak frequency, because Pearson-Moskowitz spectrum is defined based on the peak frequency. It says that the spectral energy S omega is given by alpha g square by omega phi, which is a variable, e to the power of minus 1.25 omega by omega 0 to the power of minus 4. So, where in this case alpha is called as Phillips constant, which is given by 0.081. For offshore application, this spectrum is modified. The PM spectrum, what is being described, includes a peak frequency which is omega 0 in the equation, which is actually the function of mean wind speed measured at a height of plus 19.5 meters above the mean sea level. So, the spectrum has only one parameter, to specify, which is an independent parameter it is either the peak frequency or UW, because both of them are interdependent. If I know one, I can find the other. This spectrum is further modified which is now being used in design of offshore platforms. This has two parameters, namely significant wave height and peak frequency. This equation is given by where in this equation the peak frequency is given by 2/3 of UG UW, Hs is significant wave height, and UW is the mean wind velocity. The second spectrum we have is brush index spectrum. Which again has two parameters, namely significant wave height and significant frequency, which is given by 0.1687 Hs omega s by omega e to the power of minus 0.675 omega by omega s to the power minus 4. Alternate spectrum is given by International Ship Structures Congress, which is ISSC spectrum, which is again a two parameter spectrum, which is Hs and omega bar. In this case, the spectral density function is given by the following equation: omega bar 4 by omega phi e to the power of minus 0.4427 omega to the power of minus 4, which is equation 3, where omega bar is given by m1 by m0, where mi is called spectral moments, mi can be simply given by omega I Sx plus omega d omega for I equals 0, 1, etc. People also use John-Swab spectrum, which has got 5 parameters, namely Hs, omega 0, the spectral density function is given by alpha bar g square by omega phi e to the power minus 1.25 omega by omega 0 to the power minus 4 of mu a omega. Nu is called pickedness parameter, which varies from 1 to 7. Usually an average value of about 3.3 is used in the design. This essentially obtained based on experimental studies, AW is given by exponential minus omega 0 square by 2 sigma square omega 0 square where sigma dash is actually called spectral width parameter, which is actually 0.07 for omega less than omega naught and 0.09 for all omegas more than omega 0. Alpha bar is a constant which is 3.25 into 10 power minus 3 h s square omega 04 of 1 minus 0.287 natural logarithm of Interestingly, for gamma equals 1, the John-Swart spectrum actually reduces to the conventional PM spectrum. For nu equals phi and for Tp by root significant height is less than 3.6, gamma is given by a separate equation which is 5.75 minus 1.15 Tp by root Hs. Gamma can be taken as phi if this value satisfy. For any other value of Tp by root Hs more than 3.6, this equation can be used. One can also compute the significant wave height which is related to the variance of wave spectrum. Significant wave height is related to 0th moment, which is the variance, because variance of the spectrum is also called 0th moment of the spectrum. So, if we know the 0th moment of the spectrum, can always find the significant wave height which is required in estimating the parameter gamma, because you have sigma Hs here, and then substitute back in the John-Swart spectrum to get the spectral density function distribution for all bands of omega. The next conventional load what we will take will be the wind load. For estimating wind forces, the most commonly used engineering approach is based on few assumptions. So, therefore, one can say these assumptions lead to uncertainties or complexities in estimating these wind forces. The assumptions are: when a stream of air flows with a constant velocity v, it will generate a force on a flat plate of area A. So, at a constant velocity, the plate will be placed orthogonal to the flow direction. So, wind forces are perpendicular to the exposed surface area. This force will be proportional to A into V square. So, the proportionality constant depends on various factors, but independent of area. This is proved by experimental investigations. So, therefore, wind force on a plate which is orthogonal to the flow direction can be estimated by net wind pressure, which I call as P w. P w is given by half rho a C w B square, where rho a is the mass density of air, which is about 1.25 kg per cubic meters. C w is called wind pressure coefficient. There is a very important assumption which is made in estimating the wind forces on offshore platforms. The assumption is mass density of air increases significantly due to the splash happening on the members up to a height of 20 to 30 meters above mean sea level. Hence, total wind induced force on a member or on the plate is given by F W is this multiplied by the area if the plate is kept an angle, if the plate is kept at an angle theta with respect to the wind direction, for example, let us say this is my plate, this is my angle theta, I know the projected area, I should say projected area, this becomes my wind direction. So, the wind force will be normal, okay, wind force will be normal to the plate. So, I have to find the resolved value of this in the direction normal to the plate if you know the angle theta. The wind pressure coefficient C W is generally determined under controlled stationary wind flow conditions. Usually, this experiment is conducted in wind tunnel to estimate C W. It of course depends on Reynolds number. The value usually is 0.7 to 1.2 for cylindrical members. So, wind force will have two components. One is the drag force, other is the lift force, which is given by these equations, where drag will act parallel to the wind direction and lift will act normal to the wind direction. So, this is called drag, this is called lift force. C D and C L are respectively drag and lift coefficients. In both the cases, area is measured normal to the wind surface. V z is given by an empirical relationship, which is z by 10 1 over 7, which is called 1/7 power law. Where V z is called wind speed at zth location in elevation. Z is called the location at which wind force is calculated, maybe in meters. V 10 is called the wind speed at 10 meters above mean sea level. So, this 10 meter is called datum height or reference height. Generally, wind has two components. the mean wind component which is more or less a static component. The next one is the fluctuating component, which is called the gust component. Usually the gust component is generated by turbulence in the flow field. This generally generated in 3 spatial directions. It is also a fact that the mean wind speed is far greater than the gust component. V of t has the mean component plus the gust component. It is interesting to note the spatial dependence of the mean component is only along the height. V of t is assumed to be homogeneous both in space and time. Since wind velocity has got 2 components, to generally obtain the load from gust component, one can use a gust factor. A gust factor is generally multiplied with the sustained wind speed to obtain the gust speed. Average gust factor, which we call as Fg, is about 1.35 to 1.45. So, there is an increase of about 35 to 45% in the gust speed. It is very important to note that variation of the gust factor along the height is negligible. So, people generally use sustained wind speed to calculate forces on the offshore members with usually 1 minute average wind speed. This is as per US Weather Bureau. Another interesting terminology which causes complexity in estimating wind load is fastest mile velocity. This is nothing but the sustained wind speed which you estimate and multiply this with the gust factor to obtain the fastest mile velocity. Usually in design of offshore platforms, people use 100-year sustained wind velocity of about 125 miles per hour in design. We all agree that wind is a dynamic process because it varies with both space and time. Space in sense both x, y and z. Therefore, few parameters are important. Because these parameters cause complexities in wind loads. The first parameter is the length of record. The record can be continuous, it can be intermittent with equal intervals between the observation. Can also measure the record only when the value exceeds a threshold number. So, there are many ways by which you can fix up the length of the record. For the record to be continuous, one looks for an average value, let us say V1. For intermittent, one looks for the value V2. You will see that generally V2 is greater than V1. The second issue is average time of the record. It is important to know that average time is defined as the time at which or over which the record is averaged. The third issue is that the wind spectrum becomes input in structural analysis. Therefore, the fluctuating component should be carefully defined. The fluctuation component in sense the gust factor. The fourth issue is the cross spectrum. Variation in wind velocity along the height is taken care of, but along x y, which is the variance or dependent on the spatial distribution, is an important parameter. This is generally handled by considering aerodynamic admittance function. So, friends, the next lecture we will talk about various wind spectra and aerodynamic admittance function, and then list the complexities that arise from the wind load on offshore platforms. So, in this lecture we discussed about various spectra which are used for estimating wave loads. Then we also start understanding some important limitations based on which wind forces are estimated on offshore members. Thank you very much.